So we've been talking about protons and electrons, and we're going to start with just a thought puzzle. It says this: explain why an atom will be ionized, the electron will be separated from the atom, if it's placed in a sufficiently large electric field. First of all, what direction is the electric field pointing in this picture, to the left or to the right? So which way will the electron feel a force? Okay, because we had to define electric field direction somehow. We defined it as the direction a positive would want to move. So a proton would feel a force to the right. The electron would feel a force to the left. If you make a big enough electric field, you can have a strong enough force that you can rip the electron off of the atom. Okay? So, strong enough E field can rip electron from atom. How strong? Depends on the substance involved. Metals, it's really easy. Don't need a strong force at all. They're conductors. But with air, our atmosphere, which is mostly nitrogen and oxygen and a few other trace gases, it takes roughly 3 million volts per meter. Now, that was the other units for electric field. We said you can measure electric field in newtons per coulomb, but yesterday we also proved that it was volts per meter. That's a handy one when we're talking about sparks, because 3 million volts per meter, well, 3 million volts per meter. If I divide that by 100, it's about 30,000 volts per centimeter. This is how, when we had the Van de Graaff generator, I was estimating how big the spark was, and I was saying to you, well, that's roughly that many volts. 1 centimeter spark, about 30,000 volts. I think we were getting about 3 or 4 centimeter sparks at one point, so you're pulling just shy of 100,000 volts. This might seem like a lot, Paige, but actually this particular electric field magnitude shows up quite frequently. Air ionizes very frequently. It's the crackle you hear when you pull apart clothes that come out of the clothes dryer. It's the shock that you get when you walk across a carpet on a cold winter day and then touch a metal doorknob. And lightning. Each of these effects is accompanied by light. The light occurs because the ionized electron does not want to remain free. It very quickly joins another atom, falls into an orbit, but typically it needs to lose some energy to do that, and it gives that energy as a pulse photon. Oh, John Travoltage. Where is John Travoltage, Mr. Dewick? I need to go to, oh, no, I think I have it on my hard drive, Mr. D. Let's see. Maybe, of course, John Travoltage. Let's see if we have them here, Mr. Dewick. Take that off. There's John Travoltage. Okay. You may have experienced this on a cold winter day. When you're rubbing your foot on the floor, you're actually rubbing some charges off of the earth and onto you. Light charges, they're going to gather on the outside of you. But if you get enough of a charge built up, they want to repel each other. You might have enough of an electric field built up that it's, if not 3 million volts to jump a whole meter, you might have enough of an electric field to jump a centimeter, which is only 30,000 volts per meter. So as you get close to the door, okay. John Travoltage. You've all, at least once in your life, got a shock touching a metal door. Okay, that's what's going on there. Okay? I used to have a shirt that, with that chair on a dry day, the electron affinity was just right. If I did this, I could build up enough of a charge that I could get shocks about like that to the back of my students' necks. It was great. Wonderful. You can build up using something called a Tesla coil. an electric field and create lightning when you want. All you need to do is get an electric field of about really 1.5 million volts. Will jump half a meter. That's pretty good. 3 million volts per meter. Where is my musical Tesla coil, Mr. Dewick? So this was a kid's science project. Science fair. This is about as good as it gets for a nerdy kid at a science fair, because if you look, the rest of the gym, pretty much empty. He's pulled the whole gym over to his. This is as good as it gets for a science fair. Woohoo! They're all coming to see me. So how do those work? First of all, a Tesla coil is a fairly complicated device, but basically it passes a voltage and a current back and forth to build up a resonance, and you can get some really big voltages from them, enough to ionize the air. That's step one. So you can send out a lightning bolt. Then what you do, there's another piece of circuitry that interrupts the lightning bolt so it goes off at a certain frequency. It interrupts it at a certain pulse, and our ears translate those pulses into notes. That's how musical frequency works. I have one. I bought one this year. Unfortunately, it has been a nightmare to assemble. I still have not got it to work. It has been a series of what else could go wrong disasters. I really wanted to have one for you folks, and I've put about 40 hours of my life into it, and the last step was about a month and a half ago. We thought we had it all ready to go. We fired it up, and the fuses promptly blew, and so there's a short, and I just haven't had time to take it apart. But my bucket list goal before I retire, at an assembly, I want to roll out a musical Tesla coil. Ladies and gentlemen, please rise for O Canada. Oh, come on. How could that? That's on my list. So, where would you not want to be in a lightning storm? Why? No. We by looking at the units, remember, we said that an electric field of 3 million volts per meter, that's to jump 1 meter. If you make the distance bigger, this answer can be smaller. You don't need as strong an electric field. Let's reverse it. As this distance gets smaller, you have a weaker and weaker electric field needed to ionize the air. If you make the distance that it needs to jump shorter, you don't need as big an electric field. So the worst place is to be there. I'll be very serious. If you're ever hiking and it's a humid, kind of thundery looking day, if you're hiking in the mountains, and if you ever feel the hair on your skin start to stand up, you're a few meters away from getting hit by lightning. You need to scream at your friends, life or death scream, and scream at them, drop everything. We need to run, not walk. We need to run to a lower altitude, because you're probably within about 15 or 20 meters of lightning being able to make the jump. Okay? Tree, same reason. Now, you wouldn't be in the top of the tree. You'd be down here, but this would allow the current to be conducted to the ground and then spread out through you. Same with boats. I have a sailboat. We're not so bad out in Western Canada on the west coast of the Pacific. On the east coast, especially in Florida, lightning is something you're always watching the horizon. And if you see a thundercloud on the horizon, you drop everything because your sailboat is basically a giant lightning rod, the mast. Yeah.
If you were inside it, would you be safe though? Because like a car would disperse outside.
Well, a car you're dispersing on a metal cage. Sailboats are made out of fiberglass. Not terribly conductive. There are all sorts of theories I've read, but I haven't yet seen a good scientific paper. Some people will claim clip some jumper cables onto your mast and throw the other end of the jumper cables overboard, and you'll give the current because lightning wants to travel the path of least resistance. I'm skeptical on that because that's a lot of current. I think all that would happen was just melt your jumper cables and continue the jump. I would certainly say don't be touching the mast. But, yeah. So how do you survive a lightning strike?
If you get caught in the middle of a big open field during a lightning storm, which of the following uniforms would be most likely to keep you safe? A thick wetsuit, a Superman costume, a medieval coat of armor, or your birthday suit?
What's the best to be wearing in a lightning storm? And this is very counterintuitive to people who don't have the physics background. They would say, why would you be wearing metal? Faraday cage.
If you answered medieval coat of armor, you might be a little crazy, but you'd also be right. You'd be crazy, of course, because lightning is much more likely to strike metal than rubber, fabric, or bare skin. The reason is that lightning bolts are just long streams of fast-flowing electrons looking for the easiest path from point A to point B, and no everyday material provides an easier path than metal. So why would a material that lures lightning bolts keep you safe during a thunderstorm? Ironically, for the exact same reason it attracts the lightning in the first place. Metal is a great conductor of electricity. Electrons glide so easily over metals that they barely penetrate into the surface. And if an electrical current happens to be moving over a hollow metal container, like a can or a box or even a welded coat of armor, the current won't reach the inside of the container. Physicists call this kind of container a Faraday cage, or in the case of the steel-woven clothing worn by linemen working on high-voltage wires, a Faraday suit. In fact, your car is an everyday example of a Faraday cage, which is why, despite what you may have heard about rubber tires, it's actually the closed metal chassis surrounding you that keeps you safe. It channels lightning around rather than through you. Of course, if you're away from your car and get caught in an open field during a storm, chances are slim that you'll have a medieval coat of armor or high-voltage line suit handy.
So what's your best bet, even if you're in your birthday suit or whatever you're wearing and you are stuck in a lightning storm in the middle of nowhere? What should you do? Okay, step 1, decrease your height. Crouch. Don't lie. Crouch.
In that case, whether you're naked or in costume, your body unfortunately happens to be a better electrical conductor than both air and soil, so it provides a great shortcut for traveling current. Stand upright and you're the fastest route for a descending lightning bolt. Lie down and you're the best path for current racing along the ground from a nearby strike. So the best thing to do is crouch low and keep your feet close together. Crouching low is obvious, but similarly important, when your feet are right next to each other, your legs don't make for much of a shortcut for the current to get from A to B. And even if they are the best path for the lightning, when your feet are the only thing touching the ground, then the current will most likely travel up one leg and down the other, missing critical organs like your heart, something these cows couldn't avoid.
Cows have a terrible time with lightning storms because basically their forelegs and their back legs, they act like a conducting parallel plate and they transmit almost all the power through their torso. Cows, if lightning hits even nearby cows, it's almost always fatal for cows. Humans are pretty good at surviving a nearby lightning strike. There's going to be some complications, but we're very rarely killed by lightning. Cows, not so much.
But actually, the real best thing to do is avoid lightning altogether, and head indoors when you spot a storm on the horizon.
So what if you're on, like, the grouse crack?
Get to a lower altitude, step 1.
What if you couldn't run?
Walk to a lower altitude. Like, in other words, as fast as you can with whatever conditioning you have, step 1, decrease your altitude. That would be step 1. Okay, I would probably say also, you got metal hiking poles. You're going to sacrifice those, toss those away. I know it's $20 or $30 to replace them. Toss them away. Okay. I mean, maybe if you folded them up, that might not make as big a difference. I would still be a little concerned. And I would certainly try to, if I could, avoid the taller trees, or if I'm going past like a really tall tree, I'm hustling here, getting to a lower altitude. Yeah. So, just some quick review. If we know the electric field, we can find electric force by, well, we defined electric field as the force per coulomb. So I guess that means another way to find electric force is QE. This is the shortcut version, Kevin, of Fg equals mg, where m was the mass and g was the gravitational field. This is a very similar pattern. Q is the charge, E is the electrical field. And this is, Nick, why I said charge behaves an awful lot like mass does for gravity. That's how charge behaves for electric fields and electric force. Your homework is the take-home quiz, of course. Got one more video to show you, though.